Now here is a representation of how Cortex M4 handles a simple interrupt. There could be more complex scenarios, but let us try and understand how a simple interrupt scenario is handled before we move on to other parts of the interrupt architecture in Cortex M4. So the bars that you see here are actually, consider them like this is actually a timing diagram. So the bar that you see is an event that is moving forward in time. So we have four events that you can see here. One is the interrupt request, one is the interrupt pending status, the actual interrupt status, and the controller operation, or what is actually going on in the NVIC. So for an interrupt process to begin, an interrupt has to be asserted, as we saw in our previous discussion. Assertion of interrupt could come through a peripheral, or it could come from an IO pin, as we saw. So when an interrupt is asserted, the first thing that the controller does is to set the pending bit for that particular interrupt. So every interrupt that you have, so system interrupt or peripheral, will have its corresponding pending bit in its own designated registers. Okay, so the pending bit is set here. This bar means the interrupt is asserted from, say, this point in time to this point in time. It could be any length, it could be shorter, longer, it depends. And also it also depends on how the interrupt is triggered, as we shall see in upcoming slides, where it could be an edge triggered interrupt, it could be a level triggered interrupt. Though we don't deal with level triggered interrupts in this case, it will be always edge triggered interrupts that we'll be dealing with. And then again, such interrupts could be a rising edge and falling edge. Now, once the interrupt is asserted, the controller raises the pending bit, and the pending bit is kept high until the controller actually starts working on the interrupt. Okay, that is, it actually starts executing the interrupt service routine. Before the interrupt service routine is executed, a few things happen. So once the pending bit is set, okay, so we have a thread running. So like we discussed, we have a thread running in the main, and once the pending bit goes high, some stacking operations happen here. That is, some registers automatically are pushed onto the stack automatically. That is, it is as we discussed, it is not the responsibility of the programmer to push certain registers to the stack. It is all done automatically. Once the stacking process completes, then the handler address is fetched. Now the handler address is fetched from the exception vector table. Now we'll have a look at the exception vector table in detail in the upcoming slides. So the address of the particular ISR is fetched, and then the ISR starts executing. Now, as I said, you are going to have some registers where you will have a pending bit set. So here probably you have a register which represents it's going to be a register, maybe a 32-bit register, and say a particular bit in that register is going to be set to, say, 1. Okay, once that happens, this interrupt goes into the pending state. Once the interrupt starts executing, this bit is changed to 0. Now this register is read write, so even the programmer can actually set and clear this bit. Okay, if the programmer doesn't set or clear this bit, it is automatically set and cleared by the hardware. But you can intervene here. Once the interrupt is completed, once the interrupt service routine is completed, the reverse happens. The return from ISR happens. That is, you go back to the program counter for the return address is actually loaded onto the program counter, and the program jumps back to the main thread. Before jumping back to the main thread, a complete unstacking operation happens where all the registers that were saved onto the stack are unstacked and the register values are restored. So when the thread executes from this point on, it is as if it starts executing from where it left off here. So the thread is oblivious of this whole occurrence of this particular interrupt. Now coming to the exception vector table. Now the exception vector table is a very important part of programming here, that is Cortex M4 programming or any microcontroller programming for that matter, because this consists of a lot of information that the processor needs or the controller needs for interrupt handling and also for reset handling. Now as we can see here, there are two types of exceptions. One is called the system exception and another one is called interrupts. Now as we discussed previously, the naming and the numbering convention in Cortex M4 is a bit complicated, but we'll try to understand it here. So when we are flashing a binary into the flash of a microcontroller, this is wherever the flash starts from or wherever the microcontroller starts executing its first instruction from. Now I'm saying wherever because the address is not always 0000. This can vary. So this is already flashed onto the microcontroller prior to execution, of course, and then the exception vector table becomes a very important location from where it gathers a lot of information. So as we can see, each area of the exception vector table is 4 bytes long, that is a word, if we say it's a word long, and so it jumps by 4 bytes. So the address jumps by 4. So as you can see, it's 0, 4, 8, C, 10, it's in hex. Though we are talking about exceptions and interrupts here, since we also have initial stack pointer value and reset here, so I'm mentioning it nevertheless. So we have the, and we are going to come back to this when we talk about the init process for Cortex M4 later. So we have the initial stack pointer value. So this, as it mentions here, this contains the reset value of the stack pointer and start addresses and exception vectors, right? So so initial stack pointer value is some value that is being set by the user, set by the programmer. So we have the liberty of setting the stack wherever we wish, and that is done in the initialization script. We'll see that. And then you have the address of the reset handler. So reset handler means whenever the processor starts, whenever you press the power button on your processor board, you have two things happening. First, the initial stack pointer value gets loaded, so the processor knows where to start accessing the stack from, and second is it goes into the reset handler. So this contains the address of the reset handler. Now, one distinguishing factor in the case of Cortex M4 is whatever you see here, hard fault, memory management fault, bus fault, and all these IRQs, interrupt requests and peripheral interrupts, so on and so forth, they are not generally, if you go further back and if you have worked on other microcontrollers, generally these are jump instructions in assembly. So say there's an interrupt is raised, and the controller knows that it's IRQ0. There's a jump address to the particular subroutine. In the case of Cortex M4, you have an address here. So the processor is intelligent enough to know that it has to jump to this address. So it is not a jump to the address, it is just an address. So one added benefit of this is you can program entirely in C without having to get into assembly coding, because since these are just numbers, or these are just address locations, you can actually create a data structure in C and allocate it to this memory location through your linker without having to write any assembly code. That is not the case always, but it is possible. Okay, so the Cortex M4 architecture ensures that such an approach is possible. Okay, so in two ways, that is automatic saving of registers and interrupts, as we saw, and having only addresses mentioned here instead of the jump instructions, because if you have to put jump instructions, it will be in assembly generally. So as we see, we have something called as the IRQ number, and we have something called as the exception number. When you call it as an exception number, the numbering starts from 1, 2, 3, and it goes up to 255. When it's IRQ number, for the system exceptions, it starts from a negative number. So IRQ number is -14. So IRQ is with respect to this, the interrupts, that is the peripherals and the pins. So the first interrupt is taken as 0, and rest of them go in the negative direction. Okay. Now, sorry about that. Now, when we are configuring interrupts in our programs, it is going to be this format. That is, we are going to take from interrupt number 0 and go onward. So say we have to trigger an interrupt through software. This is the number we are going to consider, that is 0, 1, 2, not this one. So we will not say interrupt number 16, we will say interrupt number 0. So exception number starts from 1 to 255, but interrupt number starts from 0. So there is a bit of confusion here, but this is what the convention is as far as Cortex M4 is concerned.